Have you ever wondered how computers perform addition? Well, in the world of digital logic and design, addition is a foundational operation, and it's primarily done in binary. Binary addition, much like decimal addition, operates on a base, but instead of base 10, it operates on base 2. So how does it work? Let's take a look at the possible combinations when adding two binary digits, also known as bits. When you add 0 and 0, you get 0. 0 plus 1 or 1 plus 0 equals 1. But when you add 1 and 1, things get a bit interesting. The result is 0, but with a carry of 1 to the next higher bit. The process of binary addition involves moving from the least significant bit to the most significant bit, adding the corresponding bits along with any carry from the previous bit. Now that we understand the basics of binary addition, let's dive into how we implement this in digital circuits. Meet the half adder, the basic building block for binary addition. In the realm of digital logic, the half adder plays a pivotal role. It's a simple yet ingenious device that takes two input bits and, like a mathematical magician, produces a sum and a carry. So, how does this mystical mechanism work, you ask? Let's break it down. A half adder has two inputs, often referred to as A and B, and two outputs, known as the sum and the carry. The sum output is the result of the addition, while the carry output is a bit that gets carried over to the next higher bit in case of an overflow. Now, let's look at the truth table for a half adder to get a better understanding of its operations. When both input bits A and B are 0, the sum and carry outputs are also 0. If either A or B is 1, but not both, the sum is 1, and the carry is 0. However, when both A and B are 1, the sum is 0, but the carry is 1. This carry is then passed on to the next higher bit, much like how you'd carry a number over while doing long addition in decimal numbers. In essence, the half adder is adept at handling the addition of two single bits. It's a fundamental component that forms the foundation for more complex binary addition systems. It's like the humble brick that builds the grand castle, the single note that composes the symphony. But you may wonder, what happens when we want to add more than one bit at a time? What if we have larger binary numbers to add? Well, that's where the story of the half adder takes a fascinating turn, and a new hero steps onto the stage, the full adder. So while the half adder may seem modest, it's a critical part of the bigger picture. Remember, even the mightiest of structures are built one brick at a time. A single half adder is great, but what if we want to add more than one bit at a time? That, dear friends, is a question for another scene. Stay tuned. This is where our trusty full adder comes into play. Just as a half adder is a fundamental building block in binary addition, a full adder is the next step in complexity and functionality. It's like the half adder's older sibling, taking everything the half adder does and doing a bit more. A full adder takes three inputs, two binary digits that we want to add together, just like the half adder, but it also includes an additional input for any carry from a previous addition. This additional input is what differentiates a full adder from a half adder, allowing it to handle more complex binary additions. The truth table for a full adder shows all possible combinations of these three inputs and what sum and carry they produce. If we take a quick look, when all three inputs are 0, the sum and carry out are also 0. When only one input is 1, the sum is 1 and the carry out is 0. With two inputs being 1, the sum becomes 0, but we get a carry of 1. And finally, when all three inputs are 1, both sum and carry out are 1. This ability to handle a carry input means that full adders can be chained together to create a multi-bit adder, a crucial component in digital systems. Each full adder takes care of one bit position in the numbers being added. The carry out from one full adder is passed on as the carry in to the next full adder, moving from the least significant to the most significant bit. The beauty of a full adder lies in its simplicity, yet it plays such a vital role in digital arithmetic. It's like a small cog in a large machine. But without it, the whole system would grind to a halt. So a full adder allows us to add multi-bit numbers, but how do we put it all together? Enter the n-bit binary adder, the powerful tool for adding n-bit binary numbers. This ingenious device is nothing more than a cascade of full adders, each taking care of one bit of the addition process. Let's take a moment to visualize this. Imagine a line of full adders, each waiting patiently for its turn to crunch some numbers. The first adder in line gets its inputs from the least significant bits of the numbers we're adding, but it also has a third input, a carry from the addition of the previous bits. But since there are no previous bits in this case, that input is 0. When this first full adder does its job, it produces a sum and possibly a carry. The sum is the least significant bit of our final result. But what about the carry? Well, it gets passed on to the next full adder in line, like a relay runner passing the baton. The next full adder now has its own 2 inputs, plus the carry from the first adder. It processes these 3 bits, producing another piece of the sum and possibly another carry. And so, the process repeats, with each full adder passing its carry on to the next. By the time we get to the last full adder, we've accumulated the sum of all the bits, and this last carry is actually the most significant bit of our result. The beauty of the n-bit binary adder lies not just in its simplicity, but also in its scalability. Need to add 8-bit numbers? No problem, just cascade 8 full adders. Working with 16-bit numbers? Just double the number of full adders. The n-bit binary adder can handle it all with elegance and efficiency. This cascading process allows the n-bit binary adder to process large binary numbers, bit by bit, in a way that's both systematic and efficient. Each full adder operates independently, but they're all connected by this relay of carries, working together to produce the final result. The sum outputs at each stage, when put together, form the complete n-bit sum. Just like a team of relay runners, each full adder plays its part, and the result is a perfectly executed binary addition. But let's not forget about the carries. These are the unsung heroes of binary addition, diligently passed from one full adder to the next, ensuring that every bit of information is accounted for. They're the glue that holds this whole operation together. And so, bit by bit, carry by carry, the n-bit binary adder weaves together the threads of binary numbers, creating the tapestry of digital computation. It's a marvel of engineering, a testament to the power of binary logic, and a key component in the vast world of digital systems. And that's how we add large binary numbers. But why does all this matter? Binary addition is more than just an interesting concept. It's a fundamental operation that holds the digital world together. It's the silent, unseen force that's at work every time you use a digital device. From processors and memory units to arithmetic logic units, binary addition is the heartbeat that keeps the digital world alive and well. Let's take a moment to recap the importance of binary addition in digital systems. You see, binary addition is similar to decimal addition, but it operates in base 2 instead of base 10. It involves adding 2 binary digits, moving from the least significant bit to the most significant bit, and incorporating any carry from the previous addition. It's a simple yet powerful process that forms the basis of many critical operations in digital systems. But binary addition isn't just about adding numbers. It's about efficient design and implementation. It's about creating systems that can perform complex calculations quickly and accurately. And that's where binary adders come in. These special combinational circuits are designed to perform binary addition with speed and precision. We discussed half adders, which are the basic building blocks for binary addition. They take 2 input bits and produce a sum and a carry. We also talked about full adders, which extend the functionality of a half adder to include an additional input carry. And finally, we explored n-bit binary adders, which allow for the addition of n-bit binary numbers by cascading multiple full adders. Understanding these concepts is essential for anyone interested in digital logic design. They form the foundation upon which more complex circuits and systems are built. So, whether you're a budding engineer or a curious enthusiast, these are concepts well worth exploring. Next time you use a digital device, remember the magic of binary addition that's happening behind the scenes. The emails you send, the photos you upload, the games you play, they all rely on the power of binary addition. Until next time, keep exploring.